really mind-blowing that we are getting close to trying to test whether the universe had an origin or not.
Welcome, YouTube. For those of you familiar with this channel, you know we've made a film series called Before the Big Bang, a link in the description below, about competing models for the very early universe. But recently, Scientific American have published an article claiming that one of those models, Loop Quantum Cosmology, and its Big Bounce, has been ruled out by recent satellite observations. Now, is this really right, or is it something more like fake news? Well, to help us figure it out, we have with us Ivan Agullo. Ivan is one of the scientists quoted in the article, and he's one of the world's leading experts on loop quantum cosmology. He was also in our very first film in the Before the Big Bang series and has been in subsequent ones. But back then, he was a postdoc at Cambridge with an office just a few doors down from Stephen Hawking. Today, he's the Associate Professor of Physics at Louisiana State University. So welcome, Ivan.
Hi, Phil. Thank you.
Okay, so Ivan, tell us, what was your reaction when you read the article?
Well, to be honest, my experience with this article has been a bit frustrating. At levels I had not experienced before, dealing with journals, in particular with journals aimed at communicating science to the public. And the story is the following. In April 9th of this year, I got an email from a journalist at Scientific American asking about my views on an article by Van Ten and collaborators recently published in Physical Review Letters. And I was quite familiar with the paper. I have read it and studied carefully. And therefore, I decided to provide a detailed response describing the merits of the article and, more importantly, explaining why the scenario considered in that article does not apply to loop quantum cosmology in particular. It applies to other scenarios, but not to loop quantum cosmology. The reason being that the analysis contains an assumption which is not met in loop quantum cosmology. I sent a letter to the journalist and received no answer at all. And so I just continue my life. And a few weeks later, a friend of mine wrote to me telling me, Ivan, I have read a paper in Scientific American written precisely by the same journalist and quoting me as agreeing that the bounds predicted by loop quantum cosmology is ruled out based on the work of Van Ten and collaborators. I was perplexed at the moment, and then I went and read the article and discovered that the journalist used the letter I sent, but focused on the part of my letter where I was praising Van Ten et al. Work, but completely ignored the crucial part where I discuss its non-applicability to loop quantum cosmology. And then, feeling misrepresented, I contacted the editors of Scientific American to express my concern. My request was initially ignored, and then I wrote and submitted a formal letter to the editor aimed to be published together with the article, and it was declined. Finally, I had the chance to discuss the situation with the editor-in-chief, who agreed to make revisions to the article. However, in my opinion, all revisions were superficial and did not address the core issue at all, from my viewpoint. And then I requested the complete removal of any reference to me from the article, because the article did not really reflect my true opinion. Surprisingly, my request was rejected again. So I was quite shocked. I had never experienced something like that before. And there is not much I can do, but at least I want to make clear to anybody listening what my actual opinion on this matter is.
Well, look, why don't, before we get into what was the problem with the article, why don't we just get into the science behind it? So just very briefly, can you describe what is loop quantum cosmology and why does it predict that we experience a big bounce rather than a big bang?
Loop quantum cosmology is, so to speak, a proposal for a quantum upgraded version of general relativity applied to the universe itself. And it happens to agree with the predictions of general relativity when the later theory works well. But because loop quantum cosmology incorporates quantum mechanics, it can be used to describe the universe in situations where general relativity breaks down. Namely, in the remote past, when the density of matter was extremely high and quantum effects are expected to be dominant. And the equations governing loop quantum cosmology reveal that these quantum effects, which are not present in Einstein's general relativity, but are in loop quantum cosmology, are able to introduce a sort of repulsive component to the gravitational interaction. And this component only kicks in, is only important when the density of the universe is extremely high. So that is the only regime where these new effects become relevant. And it was then found by different people that quite generically, these quantum effects are able to, if you want, to preclude the universe from starting or ending in a Big Bang singularity where matter would become infinite. Instead, this theory predicts that the universe experienced a bounce, which means that it was contracting before in the past until energy density, matter density and energy density reach a threshold. Then these quantum effects became important and the contraction stopped and became an expansion. And in that way, according to this theory, the universe did not begin 14 billion years ago in a bang, but instead that was the time of the bounce, and the universe existed before.
Okay, so is there any way that, if this story is true, that we could actually probe it with observations in astronomy?
I hope yes. And in fact, our understanding of the early universe has some parallels with the way we explore our prehistoric ancestors. What we do is to search for remnants like cave paintings or fossils containing insights about their activities, right? In cosmology, it happens that the cosmic microwave background radiation, which is made of electromagnetic waves that travel across the universe freely, almost non-interacting at all with matter, but they did interact with matter in the very early universe. And that interaction made the radiation to potentially retain important information about the way matter was distributed across the cosmos. Therefore, in this sense, the CMB, the cosmic microwave background radiation, is our cave painting, right? Is cosmology's cave painting, where the physical processes in the early universe left imprints, offering a very rich historical record, probably the best record that we have. By scrutinizing this radiation in detail, cosmologists have been able to not confirm, but to get strong support to a period of inflation, which could have happened in the very, very early universe. And similarly,
just to drop. So inflation, if I understand correctly, is this period of extremely rapid expansion where the universe doubled in size, many, many times in a
many
tiny
times.
fraction of a second.
Exactly. It's a hypothesized period right after the so-called Big Bang, with the universe expanded exponentially fast. And that should have left an imprint in the cosmic microwave background radiation, which seems to be there, giving some support, although the support is not conclusive, but is quite promising. But similarly, if a bounce happened before this inflationary era, it could have left also a distinctive mark on the CMB radiation. And identifying the signature maybe is subtle and challenging and very difficult, but many people, many theorists, including myself, have dedicated a substantial part of our efforts to compute the specific features expected in the CMB if a cosmic bound happened in the past.
So when we look at the CMB, we see that it's almost the same temperature across the sky with teeny tiny variations. And people plot these out, in little, we see this famous baby picture of the universe. But I'm told that there are certain anomalies, certain features of the CMB that don't quite fit the standard model of cosmology. Could they have anything to do with the bounce?
They are called anomalies rather than inconsistencies, because they are not conclusive. And maybe I should explain why they are not conclusive. And the reason is that our basic theories work only with probabilities, right? Quantum mechanics is a probabilistic theory at the fundamental level, and it can only make probabilistic predictions. So therefore, to put a quantum theory to the test, we need to do many measurements and compare the results with the probabilities that the theory are predicting. However, we can only make a certain number of measurements, in particular for the universe, because we cannot recreate the universe in the lab. The universe is what it is. We measure what is there, and that's it. Therefore, the way we can test our theories is limited. A typical example is, imagine a quantum theory predicting that a particle has only 1 in a million chances to be in a concrete location, and you go there and you measure and the particle is there. Would you rule out the theory? Well, not completely, because, you could have been lucky. Similarly, the intensity of the CMB radiation, when we look at different directions in the sky, has revealed patterns which are not exactly what the standard model of the Big Bang of cosmology is predicting. However, they are not fully conclusive because each of these anomalous features only have 1 chance in 1,000 to happen within the standard theory. So we could have been unlucky. However, we measure several of these features, and altogether they start being more significant statistically. Therefore, I think it could be silly from our viewpoint to completely diminish these features, because they could reveal new physics beyond the standard theory of the Big Bang. And we are scientists, so our duty is to explore them and try to make more predictions and try to rule out or confirm new ideas. So in particular, regarding these features, several of us, including myself, have pointed out that a cosmic bounce, in particular the cosmic bounce of Loop Quantum Cosmology, can produce features which would explain these features, these anomalies, with large significance. So they would not be any more anomalous.
So is it right to say that if you have a theory that can explain all the anomalies, then the statistical significance goes up?
Exactly, because within a theory in which you can make quantitative predictions within a concrete theory, the significances get a more defined, more concrete meaning, and they can go up. So this is what
Loop quantum cosmology is then, a potential explanation for these anomalies, that these are remnants of the bounce. Interestingly, I remember at the press conference for the Planck satellite, which for those of you who don't know, it's the most recent satellite to probe the CMB. Georges Efstathiou at the press conference says, well, these anomalies are interesting. They could be remnants of a pre-Big Bang universe. And basically you're saying, well, they are.
Exactly. I don't want to say they are. As a scientist, I want to say that there is a theory which makes these features to be very plausible. So, exciting opportunity is that they are the remnants of the Big Bang, and then we made other
remnants of the Big Bounce. You mean? Sorry.
Thank you. My brain today is a Big Bang at this time of the day.
Right. Actually, we should probably explain that the Big Bang and the Big Bounce are not necessarily in contradiction, because one definition of the Big Bang is that it's the beginning of all time, in which case it would be contradictory to a bounce. But another way to define the Big Bang is to say it's really just a theory that says the universe evolved from a very hot, dense state, in which case a bounce and a bang are actually compatible with one another, right?
Exactly. So one has to differentiate between these two commonly used notions of Big Bang. One is the singularity, in which everything did potentially begin, and the other is the hot Big Bang, in which the universe, matter and radiation appeared in the universe, and that is normally now understood to happen at the end of the inflationary epoch. So we could have a bounce, then inflation, and then this hot Big Bang where radiation and matter appeared in the universe.
So in that sense, in fact, inflation happens before the Big Bang.
In that sense, inflation happens before the Big Bang. Exactly.
Right. So let's get on to what these cosmologists quoted in the Scientific American article were looking for.
What they were investigating is what cosmologists call non-Gaussianity in the cosmic microwave background radiation. Let me tell you what that means, because it's a kind of technical word. And the idea is that the CMB radiation comes to us from different directions in the sky, and we map the intensity as a function of the direction. And the intensity of the radiation is not the same across all directions. There are small variations from direction to direction. And these variations, in fact, are believed to have a quantum origin in the very early universe during inflation or during the bounce, etc. So what these theories predict, in particular, what inflation predicts, is that if we measure the intensity of the radiation in all directions, we should see a distribution around a mean value. An average value, and then according to the direction, we will measure a bit up or a bit down. And this distribution, if we plot it in an axis, direction versus intensity, it will have a bell-like shape, like a bell. Meaning that, we will find some deviations around the average, but if we try to deviate a lot, the probability will be very small. This curve is called a Gaussian distribution, named after the brilliant mathematician Gauss. Non-Gaussianity refers to the deviations from this bell-shaped distribution. So if we measure the intensity of the radiation in different directions and plot it, and if the curve doesn't follow a bell shape, we call that non-Gaussianity. And a cosmic bounce could potentially predict deviation from a bell-shaped distribution, from a Gaussian, and therefore this is what they were looking for in the CMB radiation in this paper.
So they didn't find the signal. And the claim is, well, therefore, as I understood the claim, maybe you can correct me if I'm wrong, but the headline in Scientific American was something like, universe began with a bang, not a bounce, because they didn't find this non-Gaussianity. Could you explain why you think that it doesn't contradict Loop Quantum Cosmology?
So the non-Gaussianity predicted by different bounces depend on the details of the bounce. And in fact, Loop Quantum Cosmology does not predict significant deviations from Gaussianity in the CMB radiation. And the reason is a bit subtle, and it really lies in the specific type of non-Gaussianity predicted by the CMB. Imagine the three-dimensional universe, right? And it happens that Loop Quantum Cosmology predicts large non-Gaussianity in the distribution of matter. Imagine the density of matter in the early universe, and you start looking at different points, and you have the average, but then the small deviations around the average, depending where you look at. And that deviation, if you explore different points, do not follow a Gaussian distribution. So it is non-Gaussian. However, the non-Gaussianity itself changes a lot if we move from a patch to a nearby patch to a nearby patch. So here, non-Gaussianity can be large but positive, and nearby can be large but negative, and so on and so forth. So if we were able to resolve the scale where these non-Gaussianities are positive or negative, we could see this non-Gaussianity. But this scale, this distance scale is so small that we cannot resolve it. And what we see in the CMB is a kind of average. So each pixel of the CMB includes many small regions where non-Gaussianities are positive and negative. So in each pixel of the CMB, we just see the average, which is essentially a Gaussian distribution. So even though Loop Quantum Cosmology at the really microscopic level predicts non-Gaussianity, in average, which is what we can test in the CMB, this non-Gaussianity will not manifest. Therefore, not observing non-Gaussianities in the CMB do not rule out LQC. The other way around, this is what is in fact expected. And in particular, there are papers, articles where these features and this average have been computed, and predicting that looking at the CMB, we will not see the non-Gaussianities predicted by LQC. That doesn't mean that the paper of Van Tent et al. is incorrect. No, it's a very interesting paper, applicable to any bouncing theory in which this large non-Gaussianity do not average out, which is not the case for Loop Quantum Cosmology.
So would it be right to say that this averaging out we might think of as like oscillations that basically hide the signal that is actually there, and therefore because of this you shouldn't expect to see it? And they would it be right to say they mistakenly thought that you should expect to see it? But what you're claiming is they shouldn't.
Yes, you should not expect to see it, because these oscillations happen at a scale that we cannot resolve.
So the bottom line is it doesn't rule out the bounce, it doesn't rule out LQC, and they shouldn't really have run a headline saying the universe began with a bounce, with a bang, not a bounce. But what about this issue of the anomalies? Are there different versions of Loop Quantum Cosmology? Some will predict these anomalies and maybe some don't, just like maybe there's different versions of inflation. So does it have anything to say about specific sort of versions of the theory?
I mean, within LQC, there are two mechanisms that people have proposed to explain or to account for the anomalies. One relies on non-Gaussianity, but this mechanism, which was worked out by myself, is kind of inconclusive because the calculations did not include these rapid variations we were discussing before. So it was an idea, and I applied it to bouncing cosmologies for which the oscillations didn't happen, and for them this non-Gaussianity can account for the anomalies. But according, the analysis of Van Ten et al. Says that those cosmologies are disfavored by observations. What happens in LQC is not yet clear because one needs to include these oscillations in the calculation. There is a second mechanism, however, which has been worked out by different people, including Abhay Ashtekar and other groups, which is completely independent of non-Gaussianity, and therefore is not affected at all by the absence of the signal that Van Tent et al. Were looking for in the sky. This second mechanism is, it's a bit subtle, and would take me long to explain it, but the basic idea is that it's based on a quantum generalization of one hypothesis posted by Penrose years ago, and it's really a subtle interplay between gravity and quantum mechanics dictating what the gravitational field should have been at the time of the bounce, where the universe was very quantum. So putting together quantum mechanics and relativity, one can formulate Penrose's curvature hypothesis in a quantum manner, and that implies a choice of initial conditions for the gravitational field. Initial, if you want, so to speak, because we are at the bounds, the universe existed before. Initial for what? The rest of the...
It's the initial of your calculation, not necessarily the initial moment of the universe, right?
Initial of the future history from that point, which is a tautology. But it's a concrete quantum state, and that is able to produce features in the CMB which can explain the anomalies. Some of them, at least.
Okay, so let's just sort of final thoughts. Where do you think we are with what we know about the CMB, whether there was a bounce or not, whether we can probe quantum gravity or not, and also the biggest question of all is, did the universe have a beginning or not? Because the articles sort of seem to imply that it's sort of pointing to the fact that the universe did have a beginning, and of course, if there was a bounce, that would sort of undermine that. So where do you think we should sum up where we are at the moment?
In my opinion, many have held the belief that the universe before the inflationary epoch is beyond any reach from us. It is too far into the past for any signal to have survived. So there is no hope we can learn about that. I don't agree. And in particular, the article by Van Tent and collaborators supports my perspective. So they are taking the data and saying, this family of theories are ruled out. And that is a concrete example in the way, we can see beyond inflation.
Family of theories is the bounce without those oscillations, right?
Exactly, this family of theories. Exactly. And this shift in thinking is made possible by, advances both in theory and observations, in our observational capabilities. And, it's my opinion that the progress, in particular in loop quantum cosmology, has reached levels where we can now subject it to some degree of empirical testing. We can take the CMB and see if these signals are there or not. And of course, there is a lot of work ahead. But in my opinion, it is really mind-blowing that we are getting close to trying to test whether the universe had an origin or not, looking at the sky. And again, this discussion is an example of that. Perhaps I am too optimistic, but I always believe that optimism is the first step towards scientific discovery, right? So towards progress. Without optimism, we go nowhere, and I have the optimism.
Right. Well, it's always good to end on an optimistic note. So, Ivan, thank you so much. It's really great of you to explain all this and hopefully clear up what may be a misconception. So, thank you very much, Ivan.
My pleasure.